All right, today we're going to start our last chapter of material. Can you believe it?
No.
2 more sections and you are done with number theory, at least the learning of new material part of it. 2 more sections. So today we're going to start our chapter that's about integers. And today, and then on Wednesday, what we're specifically going to be looking at is addition and subtraction of integers. And we're going to be talking about some different models. Before I get there, let me just define what I mean by integers. So integers are the number system where I have the positives and the negatives of the whole numbers we've been working with. So I'm going to do the ... at the beginning to represent that it goes to the left sort of forever, right? And then I have -3, -2, -1, 0, 1, 2, and 3, like so. And it would continue to include beyond the whole numbers as well, right? Include all the whole numbers and beyond with the ... So kind of like when we did addition and subtraction with whole numbers, I presented you with some models and we talked about some of the properties that whole numbers had, and we're going to do the same thing with addition and subtraction with integers. So the first thing I'm going to talk about is 4 different models for addition and subtraction, well, addition specifically. One thing to sort of throw out there is that if you are doing this section of material, when you select your sections of material next time, I'm not doing anything in my notes that provides context word problems. I'm just showing you models. You don't get to do that. That's not what your presentation is. So please don't model your presentation on what mine looks like for this section, because I'm not doing that kind of a presentation. I'm just showing you what the actual concrete look of it is, okay? So let me show you the first model. This is called the chip model. So some manipulatives that you can actually purchase, which are pretty cool for kids to work with, look a lot like poker chips, and you could actually use poker chips if you wanted to. The ones that I have been most familiar with, and they were at the school I was at before, had one side that looked black and the other side looked red. You could also simply have black and red. And you might be thinking, well, why 2 colors are what you need. They don't really necessarily have to be black and red. So if you have in your possession a couple of colors, you need something besides the pencil you're working with, okay? So whatever color you have, doesn't really matter. You need something and you need your pencil, okay? And I'm going to use black and red because I can change my colors at will. Our black chips are going to be positive chips. Actually, I'll write it out. And our red chips are going to be negative chips. 2 reasons. Number 1, I'm doing it this way because your book does it this way. They use black and red. But the reason that they use black and red, and also the other reason they use black and red, is because black and red are sort of the standard positives and negatives when you work inside of financial softwares. If you've ever worked inside of Excel, maybe you've got your checkbook register, or you've done something where you've added and subtracted, maybe you've had a statistics class where you used Excel. It uses red for negative numbers, and it uses black for positive numbers. You've heard the phrase before that you're in the black or in the red. That's a financial term for being positive or negative within an account. Black Friday, do you know what Black Friday actually means? Black Friday is the day at which companies, by and large, actually start turning a profit. All the way through the year, they're in the red, they're negative. And on Black Friday, it's Black Friday, they actually become in the black in their company. Isn't that crazy? That's almost the way through the entire year. But hey, Christmas is coming. People spend money at Christmas, right? And then they make their profits. So we're going to use these colored chips. These are the ones I'm going to use anyway. If you use a different color, just specify for me what your color means, okay? So if you're using purple and green, then tell me purple is this and green is this, okay? Just tell me what they are. And what we're going to do is we're going to draw a circle that just represents sort of our mat. So if you were working with children, you'd actually have these poker chips or these manipulative chips, and they'd be working on their desk. So this circle sort of represents the desk work area. Are you with me? Okay, so when I have the 5, that's 5 positive black chips. So I have 5 chips, 1, 2, 3, 4, 5, just like that. And then I have the -3, and I've got -3 or 3 red chips. This is the image that the kids are working with. And then what they would learn and what you would recognize now too is that a black chip with a red chip These combined are called a zero pair. If you've already taken proportional and statistical reasoning, we do this with algebra tiles. We do this with our hands-on manipulatives, with our pawns. If you've not taken that class, then just ignore what I said because it doesn't relate, okay? But we talk about in that class zero pairs. It just means that a black chip and a red chip, they cancel one another out, right? They add to zero. So in your picture over here, what you're going to do is you're going to pair things up, right? And if they add to zero, they can be sort of removed as zero pairs. And what you are left with, what remains, in this case, would be 2 black chips, and this would be the number 2. All good? Okay, so concrete, hands-on, kids can play with toys, it's all good stuff, right? You can actually see and feel and touch what you're doing. The next imagery is a little more abstract. It's super similar, but it doesn't have the colors involved, okay? So it's called a charged fields model. We still have our sort of our working space. We're using circles because your book does. But what we do is that when we have 5 positives, we actually, a positive 5 as a number, we actually write down 5 positives. I know, right? Did I miss something, girls? Do you need me to clarify? Are you sure? No? Okay. So we're going to write down 5 positives. And then when we have the -3, we're actually going to write down 3 negatives. Okay, they're charges. And I do the same thing that I did before, right? A positive and a negative are a zero pair. So anytime I can pair them up, I will, to remove them. And I'm left with 2 positives for the number 2. Okay, so remember, most of our models are for the purpose of explaining what's happening, right? They're for that purpose. They're not for the purpose of using numbers that are exceedingly large at some point. We're not trying to do this for the number of 552, right? We don't want to do that. Really, really don't want to do that. But they're the why behind. Our next one is a number line model. I like the number line model because it's going to appeal to your kinesthetic learners. So we're going to pretend like, I'm going to show you what you would do physically, and then I'll show you how to write it down. So we're going to pretend like you've got a number line along the floor. I'm going to use the desks as my hash marks, okay? But you could actually put this on tape on the floor, and kids could walk this out, okay? So it says +5, so I go forward 5 desks. So Aspen's 0, right? We're starting at the numbered line at the beginning. And so then we're going 1, 2, 3, 4, 5. And then when I get to the -3, I would go back the other way, 3, right? So I've got 1, 2, 3. And where I was when I came across your path before is that I was at the number 2. I'm 2 away from Aspen where I started. So this would be the number 2. So you can walk it out. From a picture point of view, you can draw it on a number line as well. Let me change my image here. So you start at 0, right? And then there's 1, 2, 3, 4, 5. Arrows are good. There's my 5. And then I move backwards 3. You can jump count if you want, so like count by 3, or you can actually just jump to the 3 backwards. So this is the -3. And where I end up, where I land, is my answer of 2. Forward 5, backward 3. Okay. One more method. I would say it's probably the one that all the times that I work with this, people kind of go, whatever, when they get to this one. But I want you to know that there are kids who really, truly think the way that this next one works, okay? So this is about patterns. So if you think about some of you who are going to be working in the special ed classrooms, thinking about kids that have autism and things like this is one of those things that's usually really connecting for them to understand. So this is called integer addition with patterns. And so what we're going to do is we're going to start with something that we already know in terms of whole numbers, and we know how to add. So there's not necessarily a given starting spot. I'm simply going to start with 5 plus 2, right? Because I want to establish a pattern of what happens. And so 5 plus 2 is 7. And then I'm going to do 5 plus 1. My goal is eventually to get to 5 plus negative 3. So 5 plus 1 is 6. And then 5 plus 0 is 5. So all of those are just whole number addition facts. And you can see what the pattern is doing on the right-hand side, right? 7, 6, 5. What's it doing? It's going down 1 every time. Exactly. And if you look in the middle here, what is this pattern doing? It's also going down by 1 every time. So these go down 1 by, sort of in unison. And so I can actually talk about 5 plus negative 1, and I can know beyond a shadow of a doubt, because the number that came before 0 is negative 1, that the number that comes before 5 is 4. And I can do it again for 5 plus negative 2. Negative 2 is what comes before negative 1. And the number that comes before 4 is 3. And again, the number that I'm actually trying to get to, 5 plus negative 3, would land me at 2. It establishes the reality or the truth of the value by patterns. Okay? All right, a little bit of, it feels a little bit awkwardly placed in here, but we're going to talk about absolute value a little bit because it really didn't matter before because we only had positive numbers and now we have negative numbers as well, right? We didn't have positive numbers when we had whole numbers. I mean, we did. We didn't have negative numbers is what I meant to say. No negative numbers. And now that we do, we have this concept or this idea of absolute value. Absolute value is kind of a funny little thing to define. So jot this down in the little spaces that you have. The absolute value of x is x if x is greater than or equal to 0. And it's negative x if x is less than 0. It's on the screen too. Do you see it in the middle there?
Oh, yeah.
Yeah, they're right here. They just should fill in the gaps of your paper. There's a spot for them. So in the first one, it should say x, and the second one should say negative x. And the reason that that feels a little bit awkward is because I suspect somewhere along the way somebody told you that absolute values are always positive. Is that true? Okay. They didn't lie to you. That's a true statement. But this looks a little funny because it looks like it just told you something's negative, doesn't it? That second line? That's what it looks like, and I didn't. So let me explain. So this one right here says that the x values have to be positive. So numbers like 5 and 101, right? And 14, positives. So if I take the absolute value of any of those numbers, I get the same number. You're all good with that, right? No problem. Okay, here's what happens over here, though. This statement says my numbers are what? Less than 0. So what kind of numbers are less than 0? Negatives. So you have things like negative 2 and negative 500 and negative 28. Right, you've got negatives. So what happens when you take the absolute value of a negative? It becomes positive, right? So if I were to take, I'll just take the first one just so that I have it, the absolute value of negative 2, you expect that will become positive 2, right? But mathematically, that's the same as taking that negative 2 and multiplying it by a negative. Because what happens when you multiply a negative times a negative? It becomes positive. And we'll talk more about the whys and things behind that in the next section of material. But just in terms of definition, this is one way to describe it with symbols. It's also another way to think about the fact that this negative, oops, I did not mean for that to happen. This symbol right here doesn't mean negative. It means change the sign. The opposite sign. And the opposite sign of a negative is a positive. So when I write down negative x there, it's not meaning that the x value is actually going to be negative. It means that the values that you already have, which are negative, are going to change their signs. Okay? And I know that you'll forget half of what I just said because it still feels really funny when you get to your homework. You will. And we'll talk about it again when that happens, okay? But remember, that doesn't mean that I've got a negative number. It means that the negative numbers that I've got, because they are negative, right? That's what this piece right here says. I have negative numbers. I'm going to change all their signs. Now, a couple other things to notice, to be aware of. When you look at these restrictions, the first one says greater than or equal to 0. So that means that the absolute value of 0 is 0, right? And the second one says x is less than 0. So we've got all the numbers. It's not like that we can't use the number 0. Every now and then somebody says there's no absolute value for 0. There is. It's just 0. Another way to talk about absolute values is to talk about distances. It's always the distance back to the origin. So if you think about a picture of a number line, and here is 0, and here's 5, and here's -5. The reason that the absolute value of 5 is 5, and that the absolute value of -5 is 5, is because it's really measuring this distance, and these distances are both 5. Okay? Absolute values measure distances. So what we're going to do next is we're going to take some statements and we're going to attempt to classify them as true or false. And I don't necessarily expect you to get them all right, but I'm curious what you might think when you just see them. So we're going to give it a go. There are 4 statements. Try to decide if you believe that they are true or they are false. Okay? If you think they're false, it means you have to create an example that doesn't work. That's counterexample. And I'd like for you, once you get them sort of filled in as best you can guess, and you might guess, it's okay, to just compare with a neighbor and see if you have the same ideas or if maybe one of your ideas are different than the other. Okay, so take 2 or 3 minutes to try and fill those in. Okay, turn to a neighbor and compare once you get all your guesses on there and your potential counterexamples if you find any.
The B looks the same, but it's
Okay, let's see what kinds of things you are thinking. What do you think on A? True or false? It is true. It is a true statement. And I didn't ask you to justify why, so I will do that for you as we're looking at the true statements, because I'd ask you on a test, right? You'd have to tell me why that worked. The reason that that's true is because x to the 4th, power 4, will automatically make something positive, just like an x squared would. And so if the x to the 4th is positive, which it is, then the absolute value of x to the fourth is equal to x to the fourth by the definition above. The definition above says that if you take the absolute value of something positive, it's just that thing. What do you think about the second one? It is false. Did you have a counterexample, Michaela?
Negative x equals -1.
What?
It's false. Yep. If x is equal to -1, let's see what happens. So what is -1 to the fifth?
I'm confused. Where's the negative at?
Huh? Where it says negative at. We're creating a counterexample because the directions said to. The direction said if it's false, find an example that won't work. And so that's what we're doing. We're finding an example that won't work. And this is an example that won't work.
But they look the exact same.
But if you give me a second, they won't.
Okay.
I'm not quite there yet, but I'm close. What is -1 to the power 5? Yeah, it means I have 5 -1s, correct? And what is -1 times itself 5 times? It's -1. So this is the right-hand side of the equation. The left-hand side of the equation says, take the absolute value of that. Well, if you simplify, we just said that that's -1. And what's the absolute value of -1? It's 1. The problem is, compared to part A, when you raise something to a power that's odd, the signs stick around. If it was negative, it stays negative. And if you raise something to a power that's even, all your signs become positive no matter what. And that's what's different about A and B. What's different about C and D? Because they're awfully similar. Did anybody catch it? Are non-negative and positive the same thing? They're really close, but they're not quite the same. What does non-negative mean?
So like 0, 1, positive?
Yeah, it means 0 is included. So the absolute value of x is not always positive. This is false. And the counterexample is 0. The absolute value of 0 is 0. And 0 is not positive. It's not negative. It's neither. Right? Now, this one is true. It is non-negative because it's a distance. A distance can't be negative, but a distance could be 0. Distance could be 0. All right, how far do I have to go if I'm going to teach in this room 2 times in a row? Well, I don't have to go anywhere. I'm just going to stay right put, right? Distance 0. All right, so I can have a 0 distance. All right, let's talk real quick about properties of integers. These all are the same. You've seen every single one of these before. There's a new property that we get, but these are all the same. Closure of integers. Closure's like everybody's favorite one. Closure means that when you add 2 items that are integers together, you get another integer. Right? If I add 5 and -7, I get another integer. I don't get fractions. I don't get decimals. I don't get square roots, right? If I add 2 integers together, I get an integer. So this is a plus b is a unique integer. Commutative property. Do you remember which one commutative is? You reverse the order, right? So a plus b is equal to b plus a. Those earlier problems where I had 5 plus -3, I could have done -3 plus 5. It didn't matter. Think about how I operate them, right? I put colored discs in a bowl. It didn't matter whether I put the red ones in or the black ones in first. I still looked at 0 pairs when I was done. Associative means you're using 3 symbols. So I have A plus B plus C. That doesn't look like a C at all. Let's try that again. Equals A plus B plus C. Again, the association, the order of me associating items together doesn't make any difference. And then the last one, the identity property of addition. So the identity property says the following. There's a little bit more to write here, and I don't have very much space, but you have more. 0 is the additive identity element. And the reason is because 0 plus A is equal to A plus 0 is equal to A. And if you're still working on your test, I just answered one of your questions from the last test because this is exactly what one of the questions was about whole numbers. It's question number 5, actually, if you want to go back and look at it. Okay? Integer identity. All right, we get one new property. Let me show you that one new property and a theorem real quick because it's fast, and then we'll stop. This is our new property. It is the additive inverse. It means that for every number, there is something I can add to it to get back to 0. So for every A, there's a negative A. So that when I add A and negative A, I get 0. And you guys know this, right? 5 and what make 0? -5. And if I started with a negative, -7 and what makes 0? 7. So I didn't have this before because I didn't have negative numbers before, right? But now that I have them, I have this property as well. And then really quickly, 5.3. 5.3 tells us some of the things, again, that we are very well familiar with at this point. The opposite of negative A is positive A. That's the first one, which we've already made mention of today. The second one is if two values are equal and I add something to both of them, their result will be equal. We use that for extensively when solving equations. And the last one says that if I have negative A and negative B added, that I could just say what's A and B and then put the negative on the front. Okay, and we will look more about those next time, and we will do integer subtraction.